Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the magnetic field due to a spinning charge. So there is a charge which is spinning about this point with an angular velocity of omega, and the radius of the circle is r. And we have to find out the magnetic field created by this charge at this point O, which is the center of the circle. Now let us find out the magnetic field by two different methods. In the first method, we will be using the formula of magnetic field B, which is mu naught by 4 pi. If I write in vector form, then it is mu naught by 4 pi q v cross r upon r cube. This is the magnetic field created by a moving charge around it. So in this case, if we see that r vector is like that and the angle between velocity and r vector is 90 degree. So B will be equal to mu naught q by 4 pi r cube, and V small r will be equal to capital R and V will be equal to r omega, and radius is r, and obviously the angle between V and R is 90, so it would be sin 90. Okay, I am just writing down the magnitude only. So you can see that B will be equal to mu naught q omega divided by 4 pi r. Okay, so this is the magnetic field at point O. Now if we find out this magnetic field by a different analogy, in which we will consider this moving charge as a current carrying loop, and obviously you should always remember that if a charge is moving around a circle, then the average current flowing in that circular loop, which we are taking as a equivalent circuit of this path. So we are considering that this charge is moving in this circle, therefore there would be some current flowing in it, and we can assume a current carrying ring which is having a current I is equal to q omega by 2 pi. And we know that the magnetic field due to a current carrying loop at the center is mu naught I by 2r, and if I substitute the value of I as q omega by 2 pi, then magnetic field will be mu naught q omega by 4 pi r, which is exactly matching with the previous result. Okay, so now let us consider another point which is on the axis of the circle but not the center of the circle. So let us name this point as P. So what we have to do, we have to find out the magnetic field at this point P due to this moving charge. So let us first of all use the second method. If we consider a fact that I will be equal to q omega by 2 pi, where I is the average current flowing in this loop, then obviously we know that the magnetic field due to a current carrying loop on the axial point is B is mu naught by 4 pi. In fact, it is mu naught I r square upon 2 r square plus x square to the power 3 by 2. If we substitute the value of I as q omega by 2 pi, so it would be mu naught q omega r square by 4 pi r square plus x square to the power 3 by 2. This will be the magnetic field on the at the point P, if we consider it as a current carrying loop. But now let us verify this result by this method 1, in which we will be connecting them with a radius vector like that, and you could imagine that the velocity of this charge is in the plane of the circle, and this radius vector is perpendicular to the velocity. It would be like that. This is v and this will be the radius vector. This angle would be the 90. So this is r vector. So the angle between r vector and v will be 90, and therefore if we consider a fact that q, the value of magnetic field B is mu naught by 4 pi q v cross r by r cube, and if we find out the direction of magnetic field, then that direction would be like that. It would be this, because a magnetic field will be perpendicular to the plane containing velocity and r, because it is depending on the cross product of v and r. So B will be perpendicular to the plane containing r and v, and both r and v will be perpendicular to the direction of magnetic field. Now let us consider that this angle is theta. Obviously this angle would be 90 minus theta, and this angle would be theta, and this would be 90 minus theta, and this would be theta. So if we substitute the value of variables in this formula, then it would be mu naught by 4 pi q. Now v is capital R omega, okay, and the angle between v and r is 90 degree. So sin 90 is 1 and divided by r cube. So if we cancel out this r with this one, then it would be r square. Now you can see that small r is equal to x square plus r square root. So you can easily see that this result is not matching. If you substitute the value of r here, then you can see that this result is not matching with this result. And this is due to the fact that when we consider a current carrying ring, then we are finding out the net magnetic field along the axis of the ring. But this is the magnetic field which is not along the axis of the ring. In fact, its component, which is b cos theta, is along the axis of the ring. And if we find out the value of b cos theta, then you can see that cos theta will be equal to r upon small r. So cos theta is capital R upon small r, and b, which is parallel to axis, is b cos theta. So b is mu naught q r omega by 4 pi r square. So it is mu naught q r omega by 4 pi r square, and cos theta is r by r. So b parallel to axis will be mu naught q r square omega by 4 pi r cube. So this result, where r, we can say that r is under root of x square plus r square. So if we substitute the value, then b parallel to axis will be mu naught q r square omega by 4 pi x square plus r square to the power 3 by 2. So this result is exactly same as this result. So we can conclude that when we are applying this method to find out the magnetic field due to a rotating charge, so when we are applying the method of current carrying loop in this case, then we should always remember that this formula, this method would not give the net magnetic field on the axial point, which is not the center, but it would give the magnetic field which is along the axis. So it would only give a component of magnetic field which is along the axis of the ring, and not the net magnetic field. And at center point of the circle, we can apply both of these methods, because at the center point the net magnetic field is along the axis only, but at some other point on the axis the net magnetic field is not along the axis. So by using the analogy of current carrying loop, we would be getting the magnetic field which is along the axis only and not the net magnetic field. Okay, so if we wish to find out the net magnetic field, we could take the reverse component, or like we can see that if we are getting this value B parallel, then we can say that B cos theta is B parallel. So B parallel, in fact B would be equal to B parallel sec theta. So we can use the reverse component and we can find out the net magnetic field. Okay, now obviously if there are two spinning charges simultaneously, let us use another page. Let us see that there are two charges which are spinning in such a way such that they are always diametrically opposite to each other, like that. One charge is here and one charge is here. They are always diametrically opposite to each other and they are rotating with the same angular velocity omega, and we wish to find out the net magnetic field due to both of them at the axial point. So this is the axial point, and if we connect these two charges with this point, if this is R, this is R, then obviously this would be B, this would be B, where B is the magnetic field created by this charge only and B is the magnetic field created by this charge only. And this angle, if this angle will be theta, then it would be theta and this would be theta. So the net magnetic field, see, you can see that B sin theta and B sin theta will be cancelled out, and the net magnetic field will be along the axis only. So this would be B net, and B net will be 2B cos theta. So 2B, now single B was this one, B cos theta was this one, which is mu naught q r square omega by 4 pi. This is mu naught q r square omega by 4 pi, and here it would be r square plus x square to the power 3 by 2. This would be the, if we cancel out this 2 with this 4, then there will be 2 in the denominator. So this will be the net magnetic field due to both of them. Okay, and now if we use the analogy of current, so if we consider them as a current carrying loop, then the current flowing in this loop will be I, and I will be equal to 2q, because there are two charges which are revolving in this loop, 2q omega by 2 pi. So it would be q omega by pi, and the magnetic field on the axis is, due to current carrying loop, is B is mu naught into I r square upon this is 2 r square plus x square to the power 3 by 2. So B will be equal to mu naught I is q omega by pi, so it would be 2 pi, and r square plus x square to the power 3 by 2. Now you can see that the net magnetic field by both of the methods is same at this point, due to the fact that these are symmetric charges which are revolving in the same circle and they are always diametrically opposite to each other. So the net magnetic field due to the system of symmetric charges will be along the axis only, and the components which are perpendicular to the axis will cancelled out, and therefore by both analogies, by the analogy of current carrying loop and by the analogy of moving charge magnetic field, we would be getting the same answer of the magnetic field on the axial point also. Okay, so this is a very important thing to note that when you are using the analogy of current carrying loop to find out the magnetic field due to a rotating charge, then you should always consider a fact that if that charge is a single charge which is rotating in a circle, then you can use the analogy of current carrying loop to find out the magnetic field at the center without any changes. But if you are using the analogy of current carrying loop to find out the magnetic field at the axial point, then you should always remember that that magnetic field which we are getting by this current carrying loop analogy on the axial point will be only the component of the net magnetic field along the axis. It would not be the net magnetic field. In fact, it would be only a component. But if there is a symmetric charge system in which there are two charges or multiple charges which are equal and on the either sides of the center, and always on the diametrically opposite ends and rotating in the same circle with same omega, then in that case the net magnetic field by both of the analogies will be along the axis only, and you can use any of the method to find out the net magnetic field. So this was a very important concept, and in the next video I'll be bringing some more interesting topics. See you soon. Thank you.